Hello, everybody. Good morning, good evening. Um, Welcome to the final day. So I'm Andy Hooper, and I'll be presenting this final session of Earthquakes and Tectonics with Tim Wright today. So we've got 5 talks, as usual. And as usual, please put questions in the Slido, and we'll come to them at the end. So without further ado, let's get started with our first talk, and that'll be by Tim Hamling, and he'll be talking about large-scale velocity maps for New Zealand.
Thanks, Andy. I notice you've merged me with Tim again. It's
Sorry, did I?
Ian, but yeah, that's all right. So yeah, I'll talk about some of the stuff we've been doing in New Zealand. I think I can get my screen up. Trying to look at integrating, or basically taking some of the older archived INSAR data and combining it with the GNSS to try and generate some sort of interseismic velocities between some of the larger earthquakes we've having, and also then to try and take that forward to try and actually estimate the sort of national scale vertical displacement. And I'm sorry, my share screen is taking a while, but it looks like it's coming. And look at how to build a vertical deformation map for the country, linking that to, here we go. Can we see this?
Yeah, great.
Yeah, perfect. And then trying to link that and look at trying to pull out the coastal, basically vertical land movements, which we're starting to try and feed into the sort of next generation of sea level rise projections. So more or less, that's exactly what I've just said. And so I can move straight on. So starting with like the overview of New Zealand for people who I don't know. So down in the bottom of the Southwest Pacific, New Zealand is largely dominated or controlled really by the subduction of the Pacific plate coming in here from the east, which subducts underneath the North Island of New Zealand at around sort of 40 millimeters a year. But it's quite oblique. So the actual partition as you go from north to south decreases. So at the top you get a convergence of around 50 millimeters, and then it drops as you come further south to the Cook Strait and then into the South Island. So as well as the obviously the subduction, where New Zealand's quite well known, we have a lot of slow slip events. So in this figure here, these are shown in these green contour lines, and these tend to hug the lower limits of the inferred lock zone that's been basically derived from sort of 20 or 30 years worth of GPS measurements. If you look at the GPS velocity field shown on the left for the North Island, you can see this nice clockwise rotation of the forearc. As you come around towards you transition into the South Island, we then get this very nice strike slip motion across the Alpine Fault. As I said, the North Island has quite a lot going on, so we do see lots of these slow slip events varying in depth. So some of these deeper ones shown here, we've been able to capture in some of the INSAR data. So this was an ENVISAT interferogram from around 2004, where we were actually able to capture one of these deep slow slip events, which cause around sort of 3 to 4 centimeters of uplift at the surface. At the same time, along the
Ian, I can't hear you. Is there a technical problem in the back, guys, or can people hear me? So Ian, it's a problem at your end, apparently.
Andre?
Yeah.
Yes, Andy, I hear you.
Okay, good. Okay, we seem to have technical problems with Ian. I'm wondering if we should move to the next talk and come back to Ian. Maybe you can try and get this sorted out in the meantime, Ian. I'll leave it to you. Maybe logging out and logging back in again or something might work. Not sure what the best idea is. Okay. So I think if that's okay, we'll move to the next talk already, and that's by Chi O, and she'll be talking about again about large-scale processing. This time in the northeastern Tibetan Plateau. Chi, are you ready to go?
I'm waiting for the sharing option.
Sure. Okay.
Can you see my screen?
Yeah, great. Thanks.
Cool. Hello, everyone. Welcome to my talk. My name is Chi O, and I'm from the University of Oxford. In this presentation, I'm going to show you our work mapping rates of crustal strain accumulation for the northeast Tibetan Plateau. The tectonics of the northeast Tibetan Plateau is mostly dominated by these three strike slip faults: the Altan-Tak fault, the Hairan fault, and the Kunlun fault. The strike slip motion across these faults together accommodate over 10 millimeter per year of shortening across the region. Block models have that as the Altan-Tak fault approaches to the end on the east, the strike slip motion transfers into the shortening and the thrusting across the Qilianshan. And then the further eastward extrusion of materials then taken up by the Hairan fault and the Kunlun fault. However, in this study, we focus on this more tectonically complex region of the northeast Tibetan Plateau. However, the block models like this can only be as correct as the data that allow it. So previously, there were only geological and GPS measurements. The geological slip rates, which are represented by the squares, are mostly following the major boundary faults, whereas the distribution of GPS measurements, they are limited by the accessibility of the terrain. Now with INSAR, we can finally see through the mosaic and then get to the fine art. In addition to understanding the tectonics of the region, this work is also important for seismic hazard purpose. So the northeast Tibetan Plateau is a seismically active region with over 5 magnitude greater than 7 earthquakes happening in the past century and more registered in history. In particular, the 1920 earthquake resulted in over 230,000 deaths. The seismic risk is further increased with the recent development along the Silk Road, where a high-speed railway is put through the Hershey Corridor linking 7 major cities, including Lanzhou, the capital of the Gansu province. So we covered the study region with 23 frames of Sentinel-1 INSAR data, 10 ascending and 13 descending. For each of the frame, we try to build as well-connected a network as possible with 5 consecutive links per epoch, plus 3, 6, 9 months of long baseline interferograms. In total, across the 23 frames, we have between 300 and 600 interferograms per frame, going across 73 to 104 epochs and between 4 to 5 years. The interferograms are processed at high resolution of about 100 meters, and the length and the number of interferograms mean that we have a theoretical uncertainty below 1 millimeter per year. As a result, on average, 86% of the pixels were unwrapped. And for frames in the southeast corner, where it's more vegetated and less covered, the coherence is low, resulting in low pixel density, but we build more interferograms to compensate for that. In terms of data processing, we generated the unwrapped interferograms using the LIXA processing chain developed by Comet, and then take out from the unwrapped interferogram a Gaco's atmospheric model and a planar ramp to get to the flattened interferogram, which we use for time series analysis. We analyzed the time series networks with the NS-bus methods. Especially, we use the statistical products to analyze and to identify the bad interferograms, which are causing the high misfits. And then we remove those bad interferograms and refine the networks until we get a clean misfit map. Once we are happy, we invert for a linear velocity through the time series per pixel and get the associated uncertainties. The direct output from the above described processing chain are the flat line-of-sight velocity maps, which are individually referenced to somewhere chosen manually in each of the frames. As a result, we can see the bursts, offsets between the frame overlaps and between the track overlaps. The next challenge is to put all the frames into a common reference frame and at the same time preserving the high quality of the inside data, and so as to get to a coherent original velocity map. To do that, we use the GPS to help, and we try to only use the 3D GPS. For this purpose, we developed a joint inversion method where we simultaneously reduce the offset between GPS line of sight and inside line of sight, which is shown on panel B, and also reduce the offset between the frame overlap shown on panel C. These distribution of the offsets are shown on the columns on the right. The top panel G is reflecting the distribution of the GPS and the INSAR offsets on panel B, and the panel H and I are reflecting the distribution of offsets in the frame overlaps H and I on panel C. So we invert for a planar ramp per frame so as to simultaneously reduce all these offsets. And as a result, we get this. We see the residues, both for GPS and the INSAR overlaps, they all reduce to near zero. And distribution become very tightly bound Gaussian shape near zero, which is good news. We can go back and forward to see the effect of this inversion. As a result, we derive long stitched tracks, now all in the fixed Eurasia reference frame provided by the 3D GPS. The frame overlap boundaries have disappeared. Now we are only left with the track boundaries, which are expected because of the change of incidence angle across track. So for the next step, we want to look at the regional east velocity, which we derive directly from this ascending and descending data. And we also then used interpolated north map to get a vertical velocity. In this talk, we just focus on the east velocity here. This east velocity has a resolution of 100 meters and covering an area of 440,000 kilometers squares. And in terms of quality, we compare the INSAR velocity with the 201 GPS east velocity in the data coverage. And on average, the difference averages to near zero and has a standard deviation of about 1 millimeter per year, which is the combined uncertainty from both INSAR and GPS. So this is testifying for the good quality of the INSAR velocity field. From the map on the right, we can already see to the first order a big step boundary between across the Haiyuan fault. And this step in velocity is going more and more distributed as we move towards the west, towards the Qilianshan. And we are also seeing the velocity change across the Kunlun fault near Machu and more distributed deformation towards the west. Taking this east velocity map and interpolated north velocity from the GPS, we can then derive some velocity gradients. And using these four horizontal velocity gradients, we can then calculate the second invariant of the strain rate map on the right. So there are some key observations we can make from this second invariant strain rate map. First, we can see the strain accumulated along the major Haiyuan and Kunlun fault. And in particular, the highest strain seems to concentrate where the fault branches and at the fault junctions. And in addition, we are also seeing some non-negligible strain accumulation away from the faults, the major faults. Now let's zoom into parts of the strain rate map and make profiles and see where this strain is coming from. So let's first look at the Haiyuan fault, where strain is well localized. Profile 1 is across the creeping section on the Haiyuan fault. And we can see this sharp step change across the VE profile. And further to the north or the right on the profile, we can see an additional step, which is some slip partitioned by the Gulang fault in this little section. And this is accounting for this bulged extended strain patch on the right. And elsewhere on the Haiyuan fault, the strain is just localized on the Haiyuan fault as suggested by profile 2. If we move west, we see on profile 2, we can still observe some localized strain, but as we move towards profile 1, the strain is really more distributed as suggested by the almost a straight line profile across profile 1. Now, if we come to the west Chingling fault, again, we are seeing something more like a straight line, but due to the higher vegetation cover and the loess cover, the INSAR velocity field here is rather scattered. So maybe any localization would be embedded in the noise, but then to the first order, we think it's still more distributed. And due to the above mentioned reasons, it's also difficult to do geological slip rates in this area. But the distribution of the strain of the velocity map on the left is reflected in the more distributed strain accumulation on the right. Sorry, the other way. Finally, let's look at the East Kunlun fault. Again, we are seeing a localized deformation on profile 2, but then more a straight line profile across profile 1. So in summary, we are really seeing some variation of strain rate along fault, with the highest strain accumulated across the fault junctions. And so we think this is a mix of localized and distributed deformation. It turns out The recent Qinghai earthquake sequence is just outside this data coverage, and it also happened on the branch fault, which is different from the main East Kunlun fault. So maybe this is echoing the idea of some distributed faulting here. We are currently processing the next track of data to try and get to an interseismic velocity and strain rate before this earthquake happened. And so stay tuned for future results. And with that, I'll end my presentation. Thank you very much.
Thank you very much, Chi. Very impressive results. Thank you for finishing on time too. So we're going to go back to Ian now, and hopefully it'll work this time. And I'll get his name right this time. So it's Ian Hamling, and he'll be continuing to talk about New Zealand. And I think you've got about 10 minutes left, Ian. Okay, I'm not hearing you, Ian.
What about now?
Okay, yes, great.
Yeah, I think I was muted that time. So, once we get down into the South Island, so you've had the subduction of the Hikurangi subduction zone to the north, which transitions through the Cook Strait, and which is basically where we had the Kaikoura earthquake rupture to, through the Marlborough system, and then the slip transfers onto the Alpine fault. And then in the south, then we get a reversal of the subduction in the opposite direction of the Australian plate beneath the Pacific. So in the South Island, the fastest slip break fault at the moment is called the Hope Fault, which is essentially this fault here, which, although very close to the Kaikoura earthquake, didn't actually rupture. And then the Alpine fault takes up around 75% of the total plate motion, with around 10 millimeters a year of convergence that has then led to the sort of the uplift of the Alpine, of the sort of the Central Alps. The GPS in New Zealand's growing a lot. It's not ideal, but it's certainly getting better. If we look back in the sort of the 2000s, you can see this, the maps on the bottom left are the continuous campaign network. So from 2000 to 2005, it was pretty sparse in both the North and South Islands. And as we've got closer to now, there's been a big ramp up of continuous sites, mostly on the North Island, really with a focus of the Hikurangi subduction zone. But sadly, the South Island is still kind of lacked in sort of good network. To top that up, what we do in New Zealand is around every 8 years, the country gets divided up into 8, and then every year we go around and we resurvey some campaign marks to build up a sort of a detailed campaign survey. And so that's what's shown on the right-hand side in the velocity field, and that's basically a combination of the campaign and the continuous since around 1993. An added problem is that obviously since then, I said earlier, we've had all these slow slip events. And we've also had around 12 or more fairly large magnitude 6 or greater earthquakes in between. So obviously, if we're only measuring displacements every 8 years, then it can add in some additional noise terms to try and get the interseismic velocities out. So this is just a map, again, showing both islands and then showing the distribution of some of these earthquakes. As I said, this talk really will focus on Envisat. And in part, the nice thing with Envisat, if we take away these two earthquakes here, Gisborne and George Sound, which were mostly offshore, so didn't cause too much deformation on land, and we can trim the Envisat data set for the different scenes just before these sort of larger earthquakes over Dusky Sound, and also excluding Darfield and Christchurch. If we do that, when we get a reasonable around 8 years worth of so-called interseismic, where we shouldn't have too much contamination through other earthquakes. One of the problems going forward is when we start doing the same now, obviously with the Great Sentinel mission, is we've now had Kaikoura, which especially for the top of the South Island has made things very, very different. And this is just an example of a post-Kaikoura for the first 6 months afterwards. And you can see there's a lot of complex deformation patterns, hundreds of thousands of landslides, which are all, again, to try and derive these velocity fields will become challenging. So this is the data set we've managed to put together. So we've got all these tracks, there's around 20 tracks across the 2 islands. Unfortunately, we only have ascending data, and so we do have to play some tricks to try and extract the vertical deformation field. So what we've done is basically we've used stamps to generate multiple interferograms across all of these tracks. We've removed the predicted GPS velocity based on the interseismic velocity field from GPS. We then do a bunch of corrections for atmosphere and the sort of orbital issues, and we add that modeled signal back in and solve for the best fit displacement rate over that kind of 8-year time period. This is what we end up left with. On the left-hand side is essentially the full line of sight displacement field, and then what I'm showing on the right, which I'll focus on mostly, is I guess is a proxy for the vertical. So if we strip out all the horizontal from based on the GPS, then what we're assuming is the residual which is left over is basically dominated by the vertical component. The coloured dots are the continuous GPS sites that were operational at the same period as the INSAR, and we actually get a very good agreement in general between the vertical from the GPS and from the INSAR. But obviously the INSAR's got the advantage that we're able to get a more or less nationwide coverage. We do the same kind of tricks as other people have shown, where we look at the overlap regions to try and convince ourselves what we're seeing is at least somewhat real. That's just shown here. So there are some glaring areas where we get some problems, largely on the leeward side of some of the mountains. And the problem is that this is basically coming from some quite significant atmosphere that's we've not been able to correct. So this, again, this is an example from the Sentinel interferogram, but this pattern that we see frequently basically over the leeward side of the mountains and causes some quite challenging atmosphere to try and correct. And so some of this ends up bleeding through, so we do get some localized differences between the tracks. But for the most part, there's a fairly good agreement. Other issues I mentioned earlier, we have landslides in this figure. Each one of these sort of high frequency blobs, blue or red, are some of them fairly large landslides. Some are up to sort of 2 kilometers across, and so you see these throughout the alpine region. And one of the other big problems we notice is in lots of sort of the old glacial river valleys, we see these quite strong subsidence signals, which may get up to around 5 millimeters a year, and they seem to be correlated with basically abandoned river channels. And so what we think it is actually it's compaction of the old sediments within the river. This then, of course, when we try and average over bigger areas, because we don't have the sort of distribution of scatterers, adds some additional problems and additional noise in our final kind of vertical estimate. This, and I'll show that in a second. So if we look, this is a good example here. This is a profile through AA over the Alps, which in theory, based on the GPS shown by the red triangles, should be uplifting at around 5 millimeters a year. But what we see is as the INSAR, as you come into this area, we get this sudden drop in the displacement associated with these river valleys. And so that's basically the problem that I was describing. But hopefully what we could maybe assume is that in reality, what we should be looking at is perhaps something more like this, where, and hopefully using Sentinel, we might be able to get a much better sort of distribution of scatterers so that we can actually resolve the true nature. And there's a student at Leeds who's been working on this. We come to the North Island, so this is then these profiles here, D, E, and F. We again get this general subsidence of the East Cape as associated with because of the subduction zone and the interseismic locking. We do also see some very higher spatial frequency features, so through Hawke's Bay, where we have this very short wavelength subsidence signal, which again may indicate some sort of shallow locking on the subduction zone. And then finally, we have again sort of associated with the TVZ. Well, I'll probably run out of time. Let's get this. So
yeah, 2 minutes left, Green.
Okay, great. Oh, I can slow down slightly then. Whew. Right. If we look at, we've managed to extract this kind of full nationwide vertical estimate. And going forward, what's very useful for New Zealand and obviously elsewhere is trying to actually link the coastal vertical land movement into sea level rise projections, which isn't commonly done. So in New Zealand, there's probably around 250,000 people who live within 2 meters of the current high tide mark. And it's been suggested by insurance companies that the two major urban cities, so Wellington and Auckland, many properties will become probably uninsurable by 2030. So what we've basically done is to take our vertical estimate of the nationwide for the nation, and we basically extract a coastal strip at kind of 1 kilometer intervals. And basically what we do for each, basically at each point, we just grab as many INSAR or GPS points from around there, and we do a distance weighted average of the displacement. And we do that for the entire coastline. Because not everywhere's got uniform distribution, we've attempted to come up with a so-called quality factor, which kind of gives a bit of an idea of how many points have gone in to make that estimate, and also how far away from that location those points have come from. Does it make a difference? So it does. So Greg Garner in the US has been running these recent sea level rise predictions, and it definitely does make a difference. So for these 3 particular cases, so Tony Beach, which is basically in Wellington, you can see there's around a good 50 or 60 centimeters additional basically sea level rise associated with this long-term substance. Similarly, if we come to the East Coast, here's for Napier, 2 sites are actually only around 5 kilometers apart, but they actually have a very, very different vertical land movement. In the top case, they go around 1.2 meters by 2116, as opposed to sort of about just under a meter further south. And so it's these kind of data that we're trying to then use to inform local councils and hazard planners, because in some areas they're going to have to move forward their plans for when they're likely to get inundated.
Could you wrap up now, Christine?
Yeah, so I'll leave it there. And yeah, sorry for all the technical issues and the delays, but yeah, thanks very much.
Great, more impressive results. Thanks, Ian. So the third talk is going to be another large-scale processing talk. This time, Chris Rollins will be talking about the Central Alpine Himalayan Belt.
Can everyone see my screen?
Yeah.
Okay. Yeah, hi everyone. Thanks for tuning in. I'm Chris Rollins. So I'll be talking today about some work I've been doing to use INSAR and GNSS data to characterize strain accumulation rates in these Alpine Himalayan belt in the western part from Anatolia through the Caucasus into northwestern Iran. This is work I've been doing at the University of Leeds in partnership with a large team of people, including Tim and Andy, and many people mentioned here. And so to all my collaborators and everyone that's helped out, thanks very much. So as many of you may know that are watching, the tectonics of this region are in a large part influenced by the Arabian plate impinging from the south, and then the Anatolian block escaping to the west like a watermelon seed being squeezed out by your thumb. If your thumb is the Arabian plate, and so the Anatolian block is rotating and rotating counterclockwise and extruding into the Aegean Sea to the southwest. And the 2 of the major fault systems along which this occurs are the East Anatolian Fault and the North Anatolian Fault. This is left lateral, right lateral. And then there is compression off to the side in this sort of collision zone that builds the Caucasus Mountains and some other subsidiary features. And so as all of you probably know, one of the great uses of geodesy is that it helps us map how fast these faults are being loaded and where, and what that, and then we can translate that into what that might mean for earthquake hazard. So this is just a GNSS velocity plot relative to stable Eurasia up top. And so you can see that Anatolia is, for a large part, wholesale rotating counterclockwise and escaping into the Aegean. And one of the other things you can see is that the velocities pick up from nothing relative to Eurasia to basically the entire Anatolia motion as you cross the North Anatolian Fault. That means that already tells you that the North Anatolian Fault is kind of the major player and maybe the major place where you want to watch out for earthquakes, because it's the major strain accumulation zone. And so you can make that more quantitative. I mentioned strain, which is just a gradient in velocity across a distance. And if you look at strain, you can start correlating it quantitatively with measures of earthquake hazard. This is an example from California, from the San Andreas system. And you can see this is geodetic strain right on the left, and then these are two measures of earthquake hazard or earthquake potential on the middle and the right. The right one is just the rate of earthquakes at some magnitude or at and above that. And then the middle one is the total seismic moment release rate in earthquakes, so the total summed earthquake size per unit time. You can see that the three are spatially correlated pretty well. And then this is an example from nearer to our region, from within our region, from the North Anatolian, East Anatolian fault junction. You can see the strain rate from geodesy here, the total earthquake rate in each of these bins, and the total sum seismic moment in the middle. And again, they're all spatially correlated. So we can use that to try to, that gives us hope that mapping the strain will give us some insights about where earthquakes may come in the future. And so if we want to go to higher resolution and really get a good picture of what the fault is, how the fault is locked or creeping, and how much strain is building up where and how fast, we need to go to higher resolution data, and that's where INSAR comes in. So at the University of Leeds, I've been part of the LIXAR project, which helps, which processes and publishes in Sentinel-1A INSAR products and makes them available for anybody to use, interferograms. My part in it is mostly sitting back in admiration as Milan Lazetsky, Yasser Magsudi-Mirani, and people like Chi and the rest of the team process all of this Sentinel-1A data, make it look awesome. Scott Watson makes it look great, and then they go and find all the exception cases and fix those and work on those. And there's, you know, so it's a lot of work. So yeah, hats off to all of them. So in this region, we're going to be using, you know, the LIXAR Sentinel-1A products or a variant of them. And so this shows the LIXAR coverage in the ascending tracks of Anatolia through the Caucasus region. Black means we have all of the Sentinel-1A period processed, basically. And then light blue means we're just kind of getting started. So you can see we have basically all of Sentinel-1A's takes in Anatolia processed due to a long line of work of my predecessors at Leeds, and continuing through the LIXAR team now. And then on the descending track, again, we have good coverage in Anatolia temporally, and we're starting to get there going into Iran and the Caucasus and going eastward. So there are sort of a couple different ways we can turn these into motion rates, which is what we want to be able to, you know, combine and overlay on the GNSS to get to strain. The standard approach is to unwrap stuff first and then downsample or whatever, and then estimate, you know, take the time series, estimate the linear slope using something, code that does that. Our code is called LixBAS, and you just make time series. They look like GPS time series, but each one is, you know, a point on an interferogram through time as we tie it. And so if you do that, with all of these frames in the Anatolia Caucasus region, these are the velocities that you would get. You can see we have pretty solid coherence over a lot of Anatolia. Some breaks in coherence as you cross the Caucasus Mountains, which is not surprising given the high topography. And then this is the descending tracks. So we have about 90 frames that we were able to use with some amount of data. And then a few other frames that we're still working on off to the side, probably about 10 of them. The alternate approach, or an alternate approach, which Milan Lazetsky has been working on with Yasser and others, is to multi-look and filter the unwrapped or the wrapped interferograms first, and then unwrap, which might be more stable, and then use LixBAS and do the same time series through those products. And so this is with the traditional unwrapped stuff first. This is with the multi-looking first. And you can see that the coherence is a lot better in Eastern Turkey, for example. And you get basically good coherence everywhere except the high Caucasus, where it's very, very difficult to. And then this is the descending track. And so again, similar story. Oh, sorry, this is the multi-look method. So you can see a couple things in this. You can see the North Anatolian fault in the strain, kind of the velocity gradient across it, subtly yellow to blue. And you can also see the East Anatolian fault going yellow to blue. Now, the reason you don't see it very much is because each of these frames has a 0 in it, and everything is relative to that point in that frame. This is not relative to stable Eurasia. So in frame 58, there's a 0 point that might be like here, and this is just showing that this point right here is moving at, 3 plus 3 relative to it in the line of sight direction, not how the North Anatolian fault on this side is moving relative to this side, which is what we want. So to get that, we want to tie all of these INSAR frames together. This is something that slightly similar to what she talked about as far as merging frames. And so what we do, similar to what she did, is we use GNSS velocities from a variety of sources, and then we tie all the frames to them, to the GNSS, and then that kind of de facto ties the frames to each other because they're all tied to a common reference frame. So what I did as far as this is just dig through the literature and find all the GNSS velocities I could in this Alpine Himalayan belt, and a lot of that was from the GSRM 2.1 and then the UNR Midas set, which was another bunch of velocities, and then every post GSRM paper I could find, and then rotated them into the Eurasia fixed frame as long as they had the information that I could do that with. So this is all those velocities. The GSRM ones are in gray. The black ones are everything other than the GSRM. So you can see we've added some coverage here and there. Now you can see we have some outliers and some odd looking velocities here. So we want to do some quality control on those. So we have methods of culling stations with a high horizontal or vertical uncertainty, or we throw out stations that were not occupied for at least 2.5 years or weren't occupied at least 3 times if it's campaign. So when we do that, this becomes that. So you can see it starts to clean it up. And by the way, the colors are verticals. And then the other problem we want to get around is, I don't know if you can see my hands, but it's basically this issue where we have 2 velocities that are very close, from points very close together, that are at slightly different azimuths, which would translate to a massive tectonic strain. Like if you had 2 velocities going 15 degrees different directions, 5 kilometers apart, when in reality that might just be a data difference, a data problem with one or both of them. So for stations that are very close together, 5 kilometers apart, we just take the median of the velocities, including those from the same site. So when you do that, this turns into that. So you can now see we have a nice clean GNSS velocity field to tie all the INSAR to. And what we're going to do is we're going to tie all the INSAR to the GNSS and invert for the velocities and strain all at the same time using the code VELMAP, which was sort of developed by Hua Wang and others at Leeds and is used by Jonathan Weiss in a previous paper in 2020. It's just divide and conquer. You just make a triangular mesh. This is our mesh. It's about 0.2 degrees per mesh unit. And then you just invert for how all the frames are tied together, the bilinear ramps and the steps between them, and also biquadratic ramps and the strain and velocity maps across this whole region. And we do this at a resolution of about 3 kilometers for the INSAR, so the mesh size is a bit bigger just computationally, and we're going to try to push both of those smaller going forward. So this is, again, the multi-looked first data in the ascending, and then that's our fit to it without putting the ramps in. And then this is with putting the ramps in. Again, that's part of the model, but you can just, this starts to show up the contrast across parts of the North Anatolian fault better, as well as the East Anatolian faults. You can see the velocity gradient there, and then that's the fit, the model fit. So this is the data plus a part of the model. That's the ramp, and then that's the model plus that part of the model. This is the descending track data, and then this is our fit to it without ramps and everything. This is with ramps, and that's our fit with the ramps. So again, you can start to see this watermelon seed of Anatolia being squeezed out. In this case, it would be away from the descending line of sight. So it would be positive, so it's red, so that makes sense. So we're happy about that. And then this is the east component of motion that we invert for the full 3D displacement or velocity field with VELMAP. So this just shows the east, and you can see the watermelon seed extrusion of Anatolia to the west, blue in the east. Blue is westward here, and in the north component, you can see the gradual transition from positive northward to negative northward, or northward to southward, reflecting this counterclockwise motion, and also the gradual slowdown across the Caucasus. This is the verticals. They're a little bit noisier, but mostly in the null space out in the Black Sea where we have just nothing to tie anything to. You can see that they're not too dissimilar from the vertical GNSS in where we have the vertical GNSS, and we'll be working on cleaning these up even more going forward. And you can also see some anthropogenic. This is Konya Basin anthropogenic motion, so that's why that is going down fast. So this is our second invariant of our strain rate. Similar, Chi showed the same metric across Haiyan and other faults. And so you can see the strain rate shows up. The North Anatolian fault is prominently displayed in the strain rate across the top, which makes sense because of that big velocity slowdown that you can see even in the GNSS. But I'll show you what it looks like with GNSS only in a sec. And you can also see this crossroads off here on the east and North Anatolian fault junction. You can see the east one, and then you can see this continuing up into the Caucasus, as well as some action in Western Anatolia. This is probably a combination of some extension and some anthropogenic. This is the 2017 Iran-Iraq earthquake that happened right on the border between them. And there are some creeping zones in between here at Izmit Pasa and Izmit and Izmit Pasa, and we're averaging over multiple slow slip events. So as opposed to sort of temporally looking at the variability at this point, like the way Ian was talking about. But we want to get into that in the future. This just shows the maximum shear strain rate distribution. So the North Anatolian fault and East Anatolian fault are even cleaner in this. And then I'll just show you guys what it looks like. This is with, again, the same second invariant with the INSAR. This is exactly the same model, same smoothing parameters, mesh and everything, just with no INSAR. So you can see, not only do you see basically nothing outside of the North Anatolian fault, maybe a little bit East Anatolia, but you also get the wrong strain rate or a different, much lower strain rate on the North Anatolian fault. And that would affect your seismic hazard assessment on that. So the INSAR helps out a lot. And then the seismic hazard, just to intro through it a little bit from where we're going with this. This is just the second invariant compared against the locations of magnitude 6 or greater earthquakes since 1900. You can see they're pretty well spatially correlated. This is the westward propagating sequence on the North Anatolian fault. This here is the horrible Spitak, Armenia earthquake of 1988, which killed, I think, about 57,000 people. And you can see this is again the Iran-Iraq earthquake. This is the rate of crustal magnitude 5 or greater earthquakes at each point. So similar kind of plot to what I showed at the beginning with California. You can see that they follow each other pretty well, the strain rate and the rate of earthquakes, as we saw in those previous examples. And then if you want to take this into moment deficit buildup rate, you can multiply it by a locked width. You can assume 15 or maybe if another value is more appropriate, you can do a distribution, but I just assume 15 here. Just convert strain to moment buildup rate, and you can compare that to the moment release rate in earthquakes, that other plot down the center in those original plots. And again, you can see that they follow each other pretty well. You get this crossroads here, shows up nicely in both of them. And so where we want to push this in the near future is making that more quantitative, not just comparing spatially, but actually looking at how much moment releases earthquakes how much moment is being released in earthquakes per unit time, and whether it is sort of enough to satisfy to take up all the strain, to release all the strain that's being accommodated. And if not, how many, like what kind of bigger earthquakes we might expect coming down the line in the future. So I'll stop there. Thanks.
Thanks, Chris. Yeah, it's great to see all these large-scale processing maps of strain and velocities coming out. I'm going to hand off to Tim now to take over the rest of the session. I just want to encourage people to ask questions in Slido. We don't seem to have too many just yet. But great, thanks.
Great. So good morning, everybody. And yes, pleasure to introduce the next speaker, who is Zhang Fang Ma. And hopefully we'll be able to get straight on to that talk, except we've gone on to a different talk. So if I got the wrong schedule, on to you, Zhang. I think in my schedule I've got Zhang Feng next. Is that correct?
Yes.
Yeah. Okay. So we'll hand over to you. If you can share your screen.
My screen. I can share my screen.
Hopefully that will come. Your sound is not great at the moment either, but let's hope. Have you got the sharing option now?
Yes.
Okay. It sounds like we need to work on the sound. So let's swap the talk. Okay. You've got. Let's see. Give it a go. See how the sound works. Just ask all the other people in the room to mute their microphones. Yeah, we can see it, but the sound is really terrible. So I think what we're going to do is just swap the order over, and we'll switch to the final talk. We'll switch to Yu Zhang, and we'll come back to you afterwards. And if you could discuss with the technical team and sort out the sound, that would be great. Sorry for all the technical issues this morning. So I will hand over to this talk by Yu Zhang and Pablo Gonzalez. Over to you.
Thank you, Tim. Share my screen. Can you see my screen now?
Yes, we can.
Okay. Hello, everyone. This is Yu from Liverpool University. And here I will share our research about how INSAR could contribute to the understanding of the earthquake nucleation process. How earthquake nucleus is still under debate. And there are two leading hypotheses, cascading model and the pre-sleeping model. In cascading model, the earthquake nucleation is described as a stochastic process, where an earthquake is the response to the perturbation caused by the previous earthquakes. For example, the figure on the bottom left shows how neighbor-to-neighbor stress transfer between the foreshock and the eventual main shock during the 1999 Izmir earthquake. In the second model, the pre-sleeping model, it highlights the precursory smoothly fearing the occurrence of the big earthquake. For example, on ice stream fault, GPS stations identify around 10 centimeter slow steep migration in the downstream direction before the occurrence of the glacial earthquake. So how could we distinguish cascading model and the pre-sleeping model? We propose that the four-sleep evolution might provide crucial information to examine various hypotheses of earthquake nucleation mechanisms. In this research, we contribute to the debate of earthquake nucleation by using INSAR to study shallow continental seismic swarms. So what are seismic swarms? Earthquake seismic swarms are earthquake sequences without a clear mid-shock, aftershock pattern, and they don't obey typical earthquake empirical law. For example, the Gutenberg-Ritchie law. So why we think shallow continental seismic swarm is a unique opportunity to look into the earthquake nucleation process. First, seismic swarm has been observed to be dominated by aseismic process. Although there are not many examples for which we have insight during swarms, I make a compilation of 10 cases. The geodetic moment is around 50% higher than the seismic moment. This infers that a significant contribution of aseismic process, and thus provide with opportunity to investigate the role of aseismic behavior in the nucleation. Second, for continental seismic swarm at a very shallow depth, INSAR enables us to reveal the fault slip propagation at a high spatial resolution. For the very shallow earthquakes, the fault might rupture to the surface, and fissure and wrapping error might exist in erupt phases. To avoid fissure and wrapping errors, our previous paper demonstrates how to retrieve the fault of source parameter directly using the wrapped phase in a Bayesian approach. Okay, the test case introduced here is a seismic storm in Hawthorne, Nevada in 2011. This 2011 seismic storm lasted from March to September, migrated from south to the north, and contained 10 magnitude 4+ events. We identified three stages with respect to the time when the most energetic event, magnitude 4.6, occurred. A nucleation phase before the magnitude 4.6 from March 15th to April 17th. The most energetic phase spanning the magnitude 4.6 event, and the post-energetic phase until the end of September. We processed and generated 8 SAW interferograms to quantify the surface displacement. Using these 8 interferograms, we investigated the deformation mechanisms during 3 phases. In the nucleation phase, 2 interferograms show clear surface displacement signals around 4 centimeters in the Landslides direction. And the precursory slow sleep and precursory sleep and the most energetic seismic sleep are collocated? Perhaps not, because in the interferograms covering the energetic phase, the surface displacement signals are located further north. During the early post-energetic phase, the surface displacements are detected along a very narrow spatial band with clear phase discontinuities. It might suggest that there was a shallow after sleep reaching the surface. The analysis of the interferogram suggests that the fault sleep might have occurred along a fault system consisting of 2 fault planes. A southern subfault is active in the nucleation phase, and the northern subfault in the energetic and post-energetic phases. And the right figure presents the discretized fault geometry. With this geometry, we estimate the distribution of the fault sleep. We want to solve for the sleep diffusion of the fault plan. As we saw in Sami's presentation yesterday, this problem is ill-posed and they require regularizations. Usually, regularizations are done imposing with Smothian or statistics properties. Here we present an alternative physical informed regulation approach. Our regularization is based on a new empirical lab-based sleep model by Kerr et al. 2021. One advantage of this model is physically inelastic and fits the experimental data. The model features a finite stress at the rupture tip. Although the sleep distribution can be heterogeneous, analysis of published finite source model indicate that 85% of a magnitude 6 events, less than magnitude 6 events, can be mixed with an ellipse shape. And another advantage is low dimensionality. Previous inversion algorithms using Bayesian approaches allow for high complex patterns or computational intense. So this model needs only 7 parameters, which reduced a lot. We validate this model with static thesis in the context of earthquake nucleation problems. We retrieve a complex pattern by introducing several overlapping ellipses. For example, the post-like ruptures and the crack-like ruptures. This slide explains how to retrieve the high temporal resolution for sleep. We follow the idea in Gonzalez et al. 2013 and set up the linear equation. The sleep increment is the product of time span and the rate. We improved their method to solve for the sleep rate. followed by integration to get the accumulated for sleep. And the bottom figure shows the for sleep evolution from February to end of July. And you can see we have modeled observed the rapid phase very well. From the for sleep evolution from February to July, lasting for 5 months, the temporal sleep migration revealed 3 areas of with different sleeping behavior. Area 1 is in the nucleation phase, and a narrow sleep area around 5 kilometers square, and with a high sleep rate around 1.5 centimeter per day. Area 2 in the is energetic phase on the northern fault, a widened area around 15 kilometers square, and with a lower average sleep around 10 centimeters. And the area 3 is in the post-energetic phase, but just about the area 2, and the shallow sleep area around the depth is around 1 kilometer depth, and with minor average sleep rate around 0.2 centimeter per day. In the nucleation phase, the aseismic sleep dominates the fault behavior. The cumulative geodetic moment is around is equivalent to the magnitude of 5.2 event, which is 7 times of the cumulative seismic moment. The sleep evolution estimate for the Hawthorne 2011 swarm share similar peak and average sleep rate with other continental seismic swarms, and show and a slow sleeping phenomenon. For example, the slow sleeping event and episodic tremor and sleep. We know that the estimated migration velocity is lower than the other values because the time span is the longest, which is the duration between the neighboring epochs. In conclusion, the 2011 Hawthorne swarm was characterized by a nucleation phase dominated by the aseismic fault sleep behavior over a small area, which triggered the most energetic phase on the northern fault. And the 2011 Hawthorne swarm seemed to have occurred on a frictional heterogeneous fault network. Thank you.
Great, thank you. Thank you for the great presentation. We are going to try now again to switch to the talk that didn't work earlier. We're going to try with no video and with the slides being shared centrally. So we're hopeful this will work. So over to you, Zhang Fang. We've got the wrong slides though, unfortunately. So if we could get the Zhang Fang slides.
Okay, thank you.
Great.
I hope it goes well.
The sound sounds okay now, so fingers crossed.
Finger crossed.
We just need some slides. Here we go.
Thank you, Ryan.
No.
No, that's not my presentation.
Ryan is working on this in the background. We will get there very shortly, I hope.
Yes.
Brilliant.
Okay.
Right, we're there. Go for it.
Okay. Thank you. This is Zhang Fang, a second-year PhD candidate in Huahai University. Sorry for the technical issues. Today, my topics on phase unwrapping error correction and creep model uncertainty reduction. Can you hear me? Yes, I must ensure you can hear me.
Yes, we can hear you.
Okay. Yes. Next slide, please. Yes, let's introduce the scientific problem first. Okay, Ryan, the next slide. Yes. INSAR has been a rising geoptical tool to monitor the crustal motion. It measures the surface change in radiant phase ranging from -pi to pi. The recovery of those phase wrapped into this trench to their true values is called as phase unwrapping. But unwrapping error is hard to avoid. These are two examples for this. An example covering lost hills and unwrapping areas is effects on time series. INSAR phase unwrapping areas indeed lead bias to INSAR results. Okay, next slide. Yes. Let's generally introduce several methods. Current Rnp methods can be divided into 4 kinds. The first is the direct two-dimensional method. The most representative technique is NAFI. It directly unwraps interferograms one by one. Its advantage is high efficiency and accuracy, but it ignores temporal information brought by redundant interferograms. The second category is one-dimensional plus two-dimensional. The representative technique is extended MCF proposed by Pepe. It further considers temporal information. It first unwrapping all time or interferograms in the time domain, then unwrapped all interferograms in the spatial domain. Its performance can be downgraded by high deformation gradient in a short time interval. The third is two-dimensional plus one-dimensional. It first unwraps all interferograms in spatial domain, then correct all unwrapping areas in the time domain. The most representative technique is two-dimensional phase unwrapping plus two-norm method, error correction method. Its advantage is it takes just a little time, but its short back is not suitable for integer problems. The last kind is three-dimensional method. It directly unwraps all interferograms in 3D domain. The most representative technique is fit difference brought by Costantini. It can reach most reliable results, but it requires a high-performance computers. Yes, next slide. Yes, in this study, our focus is on the third method. We more focus on the error correction method. In the correction method, we focus on solving 2 issues. The first is how to correct the integer number of 2-pi error cycles. A two-norm which favors convex optimization is not the best choice. Zero norm is the best criterion. We borrow integer linear programming from compressed sensing mathematical framework to approach the performance of zero norm. The correction process is formed into a solution search for a linear equation, just show like the left upper figure. But the successful recovery of unwrapping errors is based on a priori assumption that's sparsity of unwrapping errors. That means some part of interferograms must be free of interferograms. The issue 2 is we should study the effects of unwrapping errors on the creep model uncertainty. We use the same data, but we use the different unwrapping methods. The unwrapped results provide different constraints to our creep model. So we achieved 2 creep model with different uncertainties. Okay, next slide. Ryan? Yes. Let's introduce our proposed compressed sensing 3D method. We first specially unwrap all interferograms using the prominent stems, EMCF or MCF, and or SNAFI method. Then we correct all unwrapping errors in in time domain. We use the triplet phase closure check and the integer linear programming we borrowed from compressor sensing. Each triangle is related to one error of the shown incidence metric B. The triplet phase closure can be obtained from a triangle loop labeled in the red dashed ellipse in the figure. Yes, as mentioned in the past slide, we can use integer linear programming to solve this linear equation, but since the compressed sensing needs the solution X to be sparse. Also, based on this assumption, we can obtain an exciting point that when the number of non-zero X is less than half of the rank of B, signal can be nearly 100% is recoverable. Oh, okay. Next slide. Yes, in the correction method, we should concentrate on two details in the method. Before we solve this linear equation, we must ensure L, the observation vector, is accurate. Like the displacement inversion, we need to choose a reference without displacement. Phase unwrapping error correction needs to choose a reliable region, but this region should contain at least the least, yes, or nearly zero phase unwrapping errors. We propose to use temporal coherence as an indicator because we only have selected elite scatterers instead of regular graded points. We convolve the PDF of phase 1 and the PDF of phase 2. We can obtain the phase gradients PDF. Then we integrate this PDF from -pi to pi. According to the phase continuity assumption, we can approximately obtain the probability of unwrapping correctly. We can observe from the shown figure a strong linear correlation between unwrapping accuracy and the temporal coherence can be seen from the red solid line and the red dashed line. Okay, next slide. The automatical reliable region selection can be divided into 4 steps. The first step is we must stack temporal coherence, longitude, and latitude in the matrix, and we downsample them for simplicity. Then we use the DB scan network to automatically select the reference. At last, we can obtain a reliable reference. Yes, next slide. The second detail we must pay attention is the correlation phase correction before the two-dimensional phase unwrapping. The triplet phase closure can be strictly equal to 0 for the single look data, but for multi-look data, the triplet phase closure may not be equal to 0 anymore. Then we propose to use the SVD correction method proposed by Mihalidis to correct this correlation phase, or named as fading signals. We can see the shown figure, the results before a phase unwrapping, a direction is applied. It reduces points with phase unwrapping. Yes, the more red points means the poor phase unwrapping performance. Yes, it's also indicated by the statistical cost shows in the below figure. The rationale behind is we can reduce the additional phase gradient by fading signals using the SVD correction method. It can be regarded as a mitigation. Yes, next slide. Yes, let's introduce some examples. Yes, hurry up. We choose the central San Andreas fault creep section as the example. This creep section bounded by San Juan Bautista to the northwest and Parkfield to the southeast is characterized as a nearly continuous right lateral seismic slip with a rate of up to 34.5 millimeter per year. Yes, right. Next slide. We choose accurate and efficient stems and the 3D method as a benchmark, which we choose two indicators to validate its performance. The first is the unclosed loop. Yes, it means when we label the points which triplet closure phase is not equal to 0. We also compared the two results, the root mean square error of the two results. We can see from the A and the C, the results of stems show a lower accuracy than the results we replied a correction right after the stems 3D methods. Yes, next slide. Yes, we also inverted loss velocity from these two results. It can be we selected those points with non-closed triangles in the big figure. We compared them to the GPS velocity. The mean difference and the difference STD shows a great decrease. It validates performance of our correction. It can be regarded as a gain step to the stems 3D method. We also regarded long wavelength deformation varies little over a small distance. So the change in accuracy can be measured by the standard deviation of the velocity in a 500-meter grid. The results underlying the red line indicate poor performance. Our method, this gain step, achieves a good performance in mitigating the phase unwrapping errors and improve the accuracy of loss velocity. Thank you. Next slide. Yes, we also conduct a jackknife test to inverting the creep model rate. We use two results as constraints. In this test, we used a two-layer fault model. The jackknife test is repeated 50 times. In each test, we randomly select 80% of velocity samples. We calculate the related mean inverted creep rate and the related creep rate standard deviation. The inverted two creep models only slightly differ in magnitude. Nevertheless, the calculated standard deviation of two creep rate model after correction has a significant difference. Thank you. The next slide. Okay, let's draw some conclusions. The first is we present a new method for automatically correcting unwrapping errors for INSAR time series, which supports for multi-look data. Integer linear programming from compressed sensing framework is used to calculate the integer number of phase unwrapping error cycles. The last is we reduce the creep model uncertainty of San Andreas fault creep section using proposed phase unwrapping error correction. But unwrapping error correction is not the end. We can include it and other techniques to face the challenge of big SAT data error. Yes, next slide. Let's draw some outlooks on the big SAT data era. Yes, we incorporate sequential estimator and the EMI into TOPS big SAT data consideration. we validate this near real-time workflow.
If you could
through
wrap up
geomorph-
now, your 15 minutes are up. So if you could come to a conclusion, that would be great. Thank you.
Yes. Thank you. Just slides to the last slide. Okay. Thank you, Andy. Yes. What we can share now is some code and related papers, and special thanks to Mustafa, and thank you everyone. Sorry for the technical issues. I'm sorry for that.
Okay, thank you very much for another excellent talk, and for all the speakers for their contributions in this session. So we've had some questions in the submitted, and what I'm going to try and do is go through a question per speaker, and then we will see whether we can come back to people who've had multiple questions. So we're going to start with Ian. So the question was whether you can pick up variations in rate due to transient processes like slow slip.
Yes and no. Unfortunately, with the MVSAT dataset, the acquisition timings were never particularly good. So we do struggle, although some of the deeper slow slip events we see in the final velocity maps as kind of, I guess, an averaged out signal. What we are starting to see now, some of the bigger slow slips we've had recently off the East Cape, like in 2019, we were able to pick up with ALOS 2. We managed to extract some kind of temporal evolution with that one. And also looking at some of the Sentinel of a recent slow slip that started in the last couple of weeks. It looks like, yeah, with Sentinel, I think we should be able to do it. But yeah, unfortunately, they're not with the data set that I showed.
Okay, great. Thank you. I'm going to move on with a question to Chi. So comment from Yasser Maksudi. Great work. So how do you obtain the uncertainties for each pixel?
Thank you very much. I think this might be related to another question raised by Professor Jianbao Sun. So with regards to the uncertainty of the pixel, we calculate that in 2 iterations. In the first iteration, we weight the epoch cumulated displacement with how good that interferograms associated with that epoch fit into the ramp. So how noisy the interferograms contributing to that cumulated displacements are at that place. And in the second iteration, we then weight the linear inversion, the linear velocity inversion with the uncertainty from the first iteration. So that is how bad each epoch fit into a linear velocity. So that 2 iterations controls the linear velocity, and the uncertainty from with the linear velocity is calculated as the variance of the gradient parameter from the covariant matrix times the resultant RMS.
Great. I think that probably answers, if you say, answers the other question as well from Jianbao Sun, in terms of looking at the temporal histories to look at uncertainties. So thank you for that. One of the questions for Chris then is when tying this from Sabrina Metzger. So when tying the single frame to GNSS, did you experience particular problems at the junction between the North Anatolian Fault and the East Anatolian Fault, or other places where there are sharp rate changes? So also, did you average or smooth the GNSS data when they crossed a tectonic boundary?
So the only smoothing / averaging we did is the multi-looking that we did, that Milan did, just uniformly across the entire thing. So there wasn't anything in particular done at tectonic boundaries. I am not sure whether, I don't think there were extra problems with tying to GNSS across a boundary, I can understand why that would, you would really want to make sure that the GNSS are right, kind of thing. So we may want to go back and look and maybe quality control that, the GNSS across the NAF in particular, or just make sure that that the INSAR is going right through it in profile. So that's a good idea.
Great, thank you. So there's a question for you. So interesting talk, you. Are the model parameters, are model parameter errors as well constrained using wrapped phase as they are using unwrapped phase? Oh, you're on mute.
Yes, thank you. Thanks for the question. Yes, with Bayesian approach, we could estimate the model parameters as well as the errors. If you go back to check our previous paper, Zhang and Gonzalez 2020, we demonstrated how to derive the errors and the model parameters at the same time.
Right, and do you think that it does equally well then with the wrapped phase as it does with unwrapped phase? I think that was the or better perhaps. You know, what would you think?
Yeah, I think in our demonstration case, when we are using the wrapped phase, the model uncertainty is smaller than the unwrapped phases.
Okay, great. So then there's a question for Zhang Fang. So it looks like a nice improvement. The question is, what is the computational cost like? Is this fast enough to run routinely?
Yes, the computational cost we mentioned is statistical cost provided by STEM's three-dimensionally phase unwrapping. Yes, it can be provided by Snappy method, and our method using interlinear programming is efficient. We test it over several cases. It consumes nearly 10 minutes for 3 million pixels. Yes, and it's for 465 interferograms. Yes, that's my answer. That's all.
Great, so that sounds excellent. Thank you. I think we've got time to just go over a couple of other earlier questions that didn't get answered. One for Ian. So do you have ideas going forwards for separating the long-term elastic strain accumulation, which might cause future earthquakes, from residual earthquake cycle effects?
Probably ideas, whether they're any good or not, I don't know. For some, I think beyond trying to model them out, whether through viscoelastic models for the early post-seismic, I don't have any probably great ideas. I think more and more I do think that, I guess a lot of the, now obviously we're trying to get lots of strain maps generated and things, and I do wonder when we go through into hazard, quite often the hazard models are looking at the exceedance of shaking in the next 50 years. So I do wonder in some cases whether we do need to even worry always about, we try and extract all these signals to get the background, but maybe actually some of the background for the next 50 years is important, and maybe we shouldn't always be trying to remove it. But in terms of the sort of the interseismic velocity, other than models, I don't have a great idea to help get rid of them.
Great, thank you. Yep.
Just looking on Slido, the most popular question is one to Chris from Richard Waters, and that's about the probbiness.
Right. Okay. So let's ask that question then, Chris. From Richard, so even accounting for the locations of past earthquakes, your INSAR-derived strain rate fields are much blobbier than your GNSS only ones. Presumably a lot of this is noise, and how do you plan to suppress this?
To think about that. I was just thinking about that. I haven't thought about that in a little while, and it might be possible to own the velocity is what's smoothed and the Laplacian operator is applied to it, and then I think the strain is just differentiated mesh triangle by mesh triangle. It might be possible to come up with a smoothing operator that only smooths like shear and leaves dilatation alone, and just lets it be noisy, and then we just throw that out, ignore it. Sort of a short way to do that is to look at the maximum shear strain rate, which is a cleaner distribution. And but that also, I mean, you have to know what the orientation is, and sometimes that can be very non-parallel to the fault that you care about. So I have to think about that. I realized in Sabrina Metzger's follow-up, I kind of misanswered. So yeah, thank you, Sabrina. I did not think about like the fact that we were taking the median between velocities at 5 kilometer spaces, even across like the North Anatolian Fault. I know that the GSRM only did it with 1 kilometer, within 1 kilometer, so that they didn't cross the creeping section of the San Andreas. So I've added a note: don't median across faults in my Google to-do list for this project. So thanks.
Great. I think we're going to end the session there. There are a few other questions, but I think we've covered a large number of them. We've now got a break, but I encourage everybody in the session to join the technical session that's coming up. The first half an hour or so will be a discussion on earthquakes and tectonics. And these sessions are really important just to get input from the community for things we'd like to see in the future, whether that's from future missions or how to optimize products and from ESA for Sentinel-1 and other missions. So encourage you all to join that session. You can find the link in Umbrella. I believe it's a WebEx session whereby we can all communicate. So thank you everybody, and thank you to all the speakers for a great session.
Yep, I'd like to second that. Thanks everybody, and goodbye.
Bye. Thank you.
Thank you.
Thank you.